Today we're going to talk about DmRPC, Disaggregated Memory Aware Data Center RPC for data-intensive applications. So let's start with what is RPC itself. So RPC is remote procedure call, which has been a key building block of distributed systems ever since like 80s. So the logic here is like very simple. When some application client tries to call a remote function on a server side, it makes a call, then measure it, and transfers to the transportation layer by like anything. It could be CXL, it could be Internet, it could be Wi-Fi, like anything. After unmashing it, the server executes the remote function and sends a response back. So RPC works on pass by value. So it's a lot of data transferred around. But due to its simplicity, it's very common to use on server-side applications. So now, what's DM? DM is disaggregated memory. So it could be several types. It could be network-based and CXL-based memory disaggregation. And it have several subtypes as well. So in network-based, we have page-based and object-based. Page-based is when it manages remote memory at the granularity of page. So when there is a page fault, it evicts recently unused local pages and fetches remote needed pages. In object-based memory disaggregation, everything happens on the base of the virtual memory abstraction level and swapping individual application level memory objects. For CXL-based memory disaggregation, it have two types. Logical devices fabric attached memory. It's when one CXL-based memory to have 16 logical devices inside and could be splitted, have several outspots or device physical addresses for it. So 16 different addresses. For GFAM, Global Fabric Attached Memory, has only one device physical address space that is common across all the hosts. Yeah, on the left you can see the scheme, how it looks like. So the motivation of DmRPC. So what's the issues of traditional global address space? So distributed shared memory raises some concerns. Adopting the DSM model would greatly harm agility and modularity of microservices. Introducing DSM into data centers at RPCs significantly complicates the microservice logic and couples the core equally. In distributed in-memory data store, when transferring large data, the code copies the entire data that creates a big overhead of data lying around in a network. Instead of directly using this immutable copy, this copy must be copied from its local data store to the user's heap. So several copies on the way to the destination, and that creates a big overhead in a network and in processing speed as well.
Hey, Alekbar, can I stop you for a sec?
Yes.
So we have like a distributed shared memory, right? And it's different from the disaggregated memory, right?
Right.
And so in distributed shared memory, I think what they really mean in it.
It's when you have distributed global shared address and space across physically distributed machines.
Paper is like a shared memory that itself have that memory, right? So like if you build an application, yeah, so if you're building like a microservice application, like every node or every instance of every like service will have like a chunk of that memory, right?
Yes, yes.
So that's why it's like distributed shared, so everyone has that memory. Versus in disaggregated memory, it's more like a distributed data store, right? It's like we have a microservices or like whatever components, and then we have that like DM memory kind of separate, right?
Yes.
Kind of, but not kind of, right?
Yeah.
Okay.
So yeah, what I was talking about. Yeah. So if you look at approaches at traditional RPC, so the shading semantics is passed by value that creates a low performance, but it's simple for programming. DSM model, the previous work, is passed by reference with a high performance but very complex tool for programming. In this distributed in-memory data store, the performance is very low and it's immutable. So, and there's one DmRPC, so claimed to be passed by reference, high performant, simple to program, and mutable. So the structure of DmRPC overall is just when you have microservice connected to the RPC and DM layer, and you're passing by reference all the data between DM layer disaggregated memory and the service microservice itself. So it could be done by either CXL or Ethernet or some other mechanics that we will talk now. But first of all, let's talk about the goals and overview. So the first goal of the DmRPC was minimizing redundant data movement along the network when using data center RPCs. So what's they done for this? They now not copying the data, but getting the reference to the data in a disaggregated memory and passing the reference via RPC. So instead of copying the whole chunk of data, they just sending the reference to this data, and they copying this data only on the write. That's why, and this way they solving abstract and complex user logic away from handling data consistency and introducing a trivial performance overhead. So in this example clearly shows how it works. So we have some chunks of memory A, B, and C, and clients have references to them. And when it sends some RPC code for worker to work on this data, it passes a reference to the worker. The worker connects to needed chunks like B and C in this case. So now B and C shared between client and worker one. At this point, the worker needs to write something to the B. To have it changed, it copies all data from B to a new page and makes write inside the new page. And with this model, the consistency holds. So they have some programming APIs. Alloc, L3, create, ref, map, ref are used for both CXL-based and net-based DmRPC, and lwrite and lread only for net version, because for CXL version they use native load store commands to perform these operations. So DmRPC net design. It's, by the way, do you see my mouse or not?
Yeah.
Yeah. Okay. So DmRPC net is based on the page manager and understand. So there's two key blocks here. So page manager is in charge of managing the memory of disintegrated memory, threaded and DM virtual addresses range. During the initialization, the page manager allocates a large memory and pins it. The pinned memory is used for disaggregated memory. So page manager manages the pinned memory at the kernel edge of pages. So in their case, it was like 4 kilobytes. And the pinned pages are in first in, first out order. So when the user's reference counting tracks the number of processes shading by the page. So they have kind of shaded, it's just an array of pages with a simple reference how many virtual addresses are used. So the transport layer add alloc, add free to the page manager, as well as map ref and create ref. So what is operation are doing actually? Add alloc for each process leveraging the DM. Page manager maintain virtual addresses allocation tree that records virtual addresses ranges, similar to the Linux virtual memory addresses tree. And when the process allocates the new DM buffer, the page manager looks up in VA3 to find unused memory address and returns it to the process, and then updates it in an undesk translator that we will talk about a little bit later. When a microservice reuses memory by calling R3, page manager notifies address translator to clear the translation entries in hash table. For creating ref after receiving the request, page manager adds the reference count of the corresponding page by 1. Yeah, nothing too hard in that. Yeah, and for mapping, it uses, after receiving a request, page manager uses a key in the ref object to look up in the map to get the pinned virtual addresses of shared pages. So what are these translators for? So it's for software-based translation. The first translation is handled by address translator software, and it translates DM virtual addresses to the virtual address of the pinned memory. So, and during the serve of read and write requests, after receiving a read request, address translator looks up in a hash table to retrieve the virtual address of the pinned page and returns back to the process. And during the write request, after receiving it, first lookups in a hash table to retrieve a virtual address of a pinned page. Then address translator reads the reference count of the pinned page. If the reference count is more than 1, that means that this memory address shared between several processes. So, and keep consistency, it creates new page by calling the page fault. Page manager gets new page for the address translator and passes back for the process. Yeah, that's about the net version of DmRPC. Now in CXL design, how it works. It's almost the same, but with a little modifications. Because now when you have load and store function available through CXL memory, you have a direct communication with a shared memory. So for that purposes, they created coordinated server that have the access and owns all the pages initially, and then it just shares between compute services these pages to work with. Every microservice have in DMware where it have 62-page fault handler and address translator inside itself. Frames could be referenced several times. So in CXL memory, it looks like that. So you have all pages and reference count for how many microservices are now looking to this physical page. Access could be of two types, read-only or read and write access. If the access is read and write, that means that the reference count could be only 1, because if you have to write something in this page, the only access to this page should be to 1 microservice. So if they need to write something to the page that, for example, C with read-only access, and the reference count is to what they're basically doing. They're taking this C physical page and copying it to the new one. They're copying this frame, changing the access to read-write, and then changing it. Same with the freeing. So when you try to free something, if the reference count is 1, it just deletes the data. If the reference count is more than 1, it just decrements the reference count and stops with it. So, and now some experimental evaluations they did. So the baseline for experimental evaluation was eRPC. As is basic RPC protocol with looks just like traditional pass by value, not all changes. Yeah, and they compared with RPC.NET and CXL. But according to the paper, they didn't have CXL switch, so they emulated this DmRPC CXL latency by reading some other papers and adjusting it to the reality. So they have 265 nanoseconds memory latency for CXL layer. So on the right side, you can see performance on the different number of nested RPC. So they tried to call several RPC calls nested in each other. Each RPC call had 4 kilobytes of data in it. And you can see how the throughput decreases on a normal eRPC when the RPC calls, nested calls increases. But
do they mention the size of the data that they need to pass in those RPCs?
yeah, 4 kilobytes. In one call, in one RPC call, it's 4 kilobytes.
So it's conveniently one page. Okay.
Yes. Yeah, so throughput for .NET and CXL. Although I don't believe that CXL would be so high, but they used emulation for that, so I'm not sure should we rely on this data or not. But they claim that it should be reliable. Yeah, and they got like for the 5 nested calls, they got about 40 latency for CXL when the eRPC gets like twice as much. Yeah, on the left side, they had performance of load balancer they had inside, and they tested it on the yeah, its throughput and memory bandwidth occupation on the load balance server. So they observed DmRPC delivers the highest throughput and occupies the lowest memory bandwidth because DmRPC only forwards reference rather than data. So here they sent eRPC forwards data 4K to 32K in the LB server, in the load balancer server. And the result indicate DM-aware global address space can alleviate the memory bandwidth pressure on load balancer servers that run data mover application and achieve higher request rate on these servers. So they're basically saying that throughput is like 4 or 5 times bigger than 4K load for eRPC, and the memory bandwidth is twice less. That is.
Yeah. But this is a trivial application.
Yeah.
It's like the load balancer, it doesn't do anything with the data except like pass it along, right? To like the worker, like in that example that you showed before. So
yeah.
So this is like really a trivial application where, of course, you'll get the better performance because you don't touch the data at all. Like load balancer doesn't need that, data at all.
Yeah. Also, eRPC passes it by value that creates this memory bandwidth, and DmRPC just like passes by reference. It would be obvious that like the amount of data that could be passed is like way more, and the memory bandwidth would be much less. Yeah, anyway, next experiment. So here we have Effect of copy on write. So what happens when they copying the data and they wait when they don't? So it's they have all the same except that in the copy they copying the data itself while going through the microservices, and in another way they don't. So the request rate is much higher. So if for copy it's in a range of hundreds, or for the not copy version it's like in a range of thousands, so 10 times. And the same with the request size, like and response time. So it's jumps from almost 0 nanoseconds to 200. A request size is much less because they copying only the reference, nothing more. They also compared these protocols with Ray and Spark to see what changes, and the throughput increased drastically. The Ray had only 1 kilobit per second, and for DmRPC CXL it is around 100. So again, 100 times better performance. Yeah, and the same with latency. So 10 nanoseconds for CXL and around 10 to 100,000 for Spark and Ray. And that is like big difference. They also rounded to the desktop bench with an average latency of and tested 99s and 999s tail latency under different request rates. Yeah, and it seems like after 50,000 requests, ERPC gives up, and the latency just grows way higher. When DmRPC just stays pretty steady for around like 2,000 requests per second. Yeah, and the last test was end-to-end throughput and latency on different approaches. So it says a throughput comparison of different approaches that they had. So they increase the image size, both DmRPC and DMC CXL can significantly increase the throughput, but not so bad on latency. So yeah, they're increasing the image size. For eRPC just stages throughput, but for DmRPC it changed drastically because they're passing only reference, not the whole thing. That's why it increases the throughput in. But really, what they're doing, they transferring the same amount of data just by reference. It doesn't really change anything for them. That's why the claiming that the throughput changed. Because like passing the reference, by passing the reference, they're claiming that it is the same like passing the actual data. Yeah, and latency doesn't change much because it's according to this throughput. Correspond to the throughput. So since the throughput didn't change for eRPC, the same happens here. Yeah, that's pretty much it for me.